Okay, so this first question, evaluate the integral of y root x, where r is the region in the first quadrant bounded by this. Okay, so first thing I do is I draw the region. So I have x squared, looks like this. 2 minus x squared looks like this. And I'm only drawing the first quadrant because it says in the first quadrant. Okay, so I want to integrate. I'll do vertical strips first. So I'm integrating from x squared up to 2 minus x squared, same function. So here I'm integrating in a vertical direction, so I'm integrating with respect to y, and then I'm adding all of these slices up from 0, from x equals 0, all the way up to, I need to figure out where they intersect. 2x squared equals 2, x equals plus minus 1. So that's going to happen at 1. So I'm integrating from 0 to 1. Okay, so I evaluate this. This is separable, so I can bring the 2 all the way out in front. And then this root x has nothing to do with, it doesn't depend on x. So as far as y is concerned, it's a constant. I can bring it out of this. And then I can factor the integral with respect to y. No, I can't because of the bounds. Okay, that's fine. So integrating from 0 to 1, root x times the integral from x squared to 2 minus x squared of y dy dx. Okay, and I can't pull this out because the bounds depend on x. So integral of y is y squared over 2. So I have root x times y squared over 2 from x squared to 2 minus x squared. Dx. Okay, so this is from 0 to 1. 2, integral from 0 to 1. So I have root x. The 2 is going to cancel out, so I'll cancel those out. And then I have 2 minus x squared minus x squared dx. And then working this out, I have integral from 0 to 1, root x times, that's going to be 4 minus 4 x squared plus x to the 4th minus x to the 4th. Those cancel. And then I'm finally left with, let's see, I can factor a 4 out. Integral from 0 to 1 of root x minus x to the 5 halves dx. So then we integrate this. We have 4 times, so that's going to be x to the 3 halves, no, to the 3 halves times 2/3 minus x to the 7 halves times 2 over 7 from 0 to 1, which gives me 4 times 2 over 3 minus 2 over 7. For a final answer of 4 times 14 minus 6 over 21. 14 minus 6 is 8. 8 times 4 is 32 over 21, which is correct. Okay, that's a 3. Next one. Okay, so here it says to evaluate this. Now, I have no clue how to integrate sine of pi x cubed with respect to x. Okay, but maybe if I integrate this with respect to y first, it will become simpler and I actually have a chance. So I need to switch the bounds. So for this, I need to draw the bounds. Square root of y looks like this, and y equals 3 looks like this. Oh, I'm sorry, that's not y equals 3. That's x equals 3, right? Because this is from x equals root y to x equals 3. So they're going to cross somewhere, but let's just draw it like this. So it's going to be oh, no. So what this is describing is the horizontal slices from here to here. And those go all the way up to 9. So this is 9, and this is 0. And then we're going from x equals root y up to x equals 3. Okay, so now instead of horizontal strips, I want to do the same thing, but instead in terms of vertical strips. So let me rewrite this. Instead of x equals root y, I have y equals x squared. So now I'm going from 0, I'm doing vertical strips, from 0 up to y equals x squared. And that's the same function. But now we're integrating with respect to y, and then I want to integrate that from 0 here up to x equals 3 dx. Okay, so this doesn't depend on y. I can factor out. It's a constant. So this becomes the integral from 0 to 3 sine pi x cubed 0 to x squared dy dx. Okay, so I do that inner integral and I get 0 to 3 sine pi x cubed times y from 0 to x squared dx, which is the integral from 0 to 3 sine pi x cubed times x squared. So now I do a u sub. U equals pi x cubed du equals 3 pi x squared dx. So if I multiply and divide by 3 pi, then I have my du, and this becomes, oops, I forgot one more thing. No, I didn't. Okay, so then this becomes 1 over 3 pi, the integral. So I need to change the bound. So at 0, it's 0. And at 3, this becomes 27 pi. And then I have 3 pi x squared dx, that's my du. And I just have sine of u du. Okay, so integrate, we have 1 over 3 pi. Integral of sine is negative cosine from 0 to 27 pi. So that's 1 over 3 pi minus cosine of 27 pi minus cosine of 0. That I know is 1. Okay, so cosine of 27 pi. So I know I have a 1 in there, and I have minus. Cosine of 27 pi is what? So if I have cosine of pi, it's either going to be plus or minus of a, if I have cosine of an integer times pi, it's going to be plus or minus 1. So 0 pi, 2 pi, 4 pi, those are all 1. And pi, 3 pi, 5 pi, those are all negative 1. So this is going to be plus 1. Cosine of 27 pi is going to be negative 1. So that's 1. That gives me 2 over 3 pi, which is correct. All right, next problem. Find the volume of the solid that is bounded above by the paraboloid, okay, below by the xy plane, and on the sides by the cylinder. Wait, what? So if we have the xy plane, then this is going to be coming up over the top like a parabola, okay. We have x squared plus y squared equals 4. That's this. It's a cylinder. Oh, this is a weird shape, I see. Okay. It says below by the xy plane, so that's this. So we have this on top, this on the side, this on bottom. By the YZ plane, okay. Oh, this is hard to draw. Okay, so let me go ahead and convert this to cylindrical coordinates to see if this makes things any easier. Okay, so I have, actually, I really should draw this first. So the plane y equals x, y equals x, so that's a vertical. Oh, I see. Okay, so let me also draw this looking down. So this is z and y. Okay. Yeah, and then looking down, looking straight down, I even said to do this in class. So we have, this is our cylinder, and the line y equals root 3x, that's going to look something like this. So if this is x and this is y. So it's bounded below by this, the YZ plane. Okay, so that's this axis right here. Okay, so it's basically like a wedge. So we basically have a wedge. Right, so it's going to be this kind of standing up, and it's going to look like a tall wedge. Okay, so I should figure out what the bounds are. Also, I should change everything to cylindrical coordinates. So I have r equals oh sorry, no, x is equal to r cosine theta, y equals r sine theta, and z equals z. Okay, so that gives us that this top sphere, shell right here is the equation z minus z equals 8 minus r squared. Okay, so that's this top one. We know that the cylinder, that's going to be the bound that r equals 2. Okay, so yeah, so r is going to go from 0 to 2 from the inside to here. And then we also have this other one. So that's going to be root 3 times y. Y is our sine theta equals our cosine theta, right? Y equals x. Cancel the r's, and I have tan theta equals 1 over root 3. I don't remember what tangent that is, so no, I know that if I have 1, 2, root 3, it's pi over 6. Okay, chat says pi over 6. Is that right? I'm going to assume that's... Oh, because I drew that wrong. Yeah. Yeah, that's pi over 6. Okay, so that means that theta goes from pi over 6 to pi over 2. So theta goes from pi over 6 to pi over 2. So r, it's going to start here at the origin, and it's going to go out to the boundary of the cylinder. And z, right, we know what we have. It starts at the bottom at z equals 0, right, at the xy plane. And it goes up to 8 minus r squared. So, and we want the volume of this solid. So we're going to integrate. Let's go with respect to z first. So this is 0, 8 minus r squared. I have 0 to 2, and then 0 to 0 to pi over 2. No, pi over 6 to pi over 2. dz, dr, d theta, but I changed to polar coordinates, so I need to remember to integrate r here. Okay, so none of this depends on theta. I can pull that out, so I'm going to have pi over 2 minus pi over 6 times the double integral from 0 to 2, 0 to 8 minus r squared, r dz dr. Okay, pi over 2 minus pi over 6, that's going to be 2 pi over 6. Yeah, that's just pi over 3. Oh, duh, of course that's pi over 3. Okay, times the integral from 0 to 2. We integrate r, we get r squared over 2. Nope, we're integrating with respect to z first. Integrate with respect to z, we get rz from 0 to 8 minus r squared, dr. So we plug that in, we have r times 8 minus r squared, dr, equals pi over 2, 8r minus r cubed, dr. That's going to be, let's see, so we have 8r squared over 2, so that's going to be 4r squared. Minus r to the 4 over 4 from 0 to 2. And plugging everything in, we have pi over 2 times, so we plug in 2, we get 16 minus, let's see, 2, 4, 8, 16 over 4 minus 4. That's 12 over 2, so that's going to be 6 pi. Answer says is 4 pi. Say what? Oh, yeah, I see that. Yeah, I switched from pi over 3 to pi over 2. Oops. That would make the difference. Yeah, this is 3, 3, 3 over 3. So yeah, 12 over 3, that's 4 pi. Thank you very much. Cool. Next one. Okay, so it just says evaluate. Doesn't look like there's anything crazy about this one. We just need to plug and chug. So this is going to be integral from -1 to 1, integral from 0 to x, and then I'll evaluate this integral with respect to z. So this is going to be 6z squared over 2, so that's 3z squared plus 3yz from 0 to xy dy dx, which is integral from -1 to 1, 0 to x. So we have 3x squared y squared plus, this is z, 3xy squared. And then at 0, we just get 0 for both of them. Okay, so actually I can factor out the y squared, and that, that doesn't really do me much. I'll go ahead and just integrate this. So if I integrate this with respect to y, I get y squared, sorry, x squared y cubed over 3, the 3's cancel out, plus x y cubed, again the 3's cancel out, from 0 to x dx, -1 to 1. Plug the x's in, and I get x to the 5th minus x to the 4th dx. So the integral of x to the 4th, since that's an even function, is going to be, sorry, integral of x to the 5th, since this is an even function, is going to be 0. So that's just going to be minus 2 integral 0 to 1 x to the 4 equals minus 2 over 5. That doesn't look right. I get a negative. Where's my negative coming from? Oh, because that's positive. Yeah. So that should be plus. Cool. Next question. Let S be the solid in the first octant bounded by the cylinder y squared plus z squared equals 1, and the planes y equals x equals, okay. So in the yz plane, this is a circle. I have the planes z equals 0. So that's the xy plane. So that's going to be this here. So we have the top half of the sphere. The plane x equals 0. That's going to be this plane straight up along here. No, that's y equals 0. I should draw this in the xy plane also. So in the xy plane, what do we have? Y equals x equals 0, and let's see, so this is y, and this is x, and what's my other bound? Y equals x equals 0, cylinder. Okay, so I'm integrating with respect to x. So, oh, I see. Okay, so we're gonna have a cylinder kind of going around the x-axis. So that's like this. No, y squared. What does this region look like? Okay, so we have this. Z equals 0 is the xy plane, so that's going to be the top half of this cylinder. So we have a cylinder coming up out of the page, and we go from x equals 0 is the bottom, and how high up does it go? It goes up to x equals y. Oh, I see. Okay. Yeah. Okay, so this is going to be, so I'll do the part that I can see first. Actually, the part that I can't see first. So I know that x comes up out of the page. It goes from 0 up to y, right? Because we have x equals y. 6z dx, so that's the part that I can't see. And now I can do this part that I can actually look at. So we're going from 0, so we're going from the line y equals 0, sorry, z equals 0, up to, what is this? This is z equals 1 minus y squared. Let's give myself some more room. Just going to give myself some more room. So we have the integral. So we said x goes from 0 to y dx. Y goes from 0, or sorry, z goes from 0 to root 1 minus y squared. So that's z. And then y goes from here, the line x equals 0. Or is this what I was looking for? Okay, no, so it is this whole top half. So that's going to go from -1 to 1. That's what was confusing me. So in the xy plane, right, we have this, but it goes from -1 to 0. Oh, because it has to be bounded by the plane. Okay, yeah. So because it's bounded by this plane, y equals x and x equals 0, it's kind of like this region right here. Okay, let's see if I get this right. I'm going to say this is from 0. It might be from 1. But this is a very strange domain. Would it be easier to change coordinates? No, it might be. What would that look like? We'll see. Okay, so I integrate this with respect to x, and I get um, 6z x from 0 to y dz dy is the integral from 0 to 1, 0 to root 1 minus y squared of 6 zy dz dy. So I integrate this with z, and I get 6, or z squared over 2. That's going to cancel, so I get 3 z squared y from 0 to root 1 minus y squared dy. Plug that in and we get integral from 0 to 1, 3 times 1 minus y squared y dy. So we have 3 integral 0 to 1 y minus y squared dy, which is 3 times 1/2 minus 1/3, which is 3 times 1 over 6, which is 1/2. Is that right? I hope that's right. That is not right. What would it be if I went from -1 to 1? Let's see if that was the problem. So this would be minus 1/3 minus, we plug in -1, we get hold on. I can't do that in my head like that. So this is going to be 3 times y squared over 2 minus y cubed over 3 from -1 to 1 equals 3 times 1/2 minus 1/3 minus 1/2 plus 1/3. Right, because when I plug this in, it's, yeah, okay. So that becomes, let's see, the 1/2s cancel. That's not right either. Okay, so something is going on with my domain. Does anybody in the chat disagree with my domain? Because I don't agree with it. So we have the planes y equals x, y minus y cubed. Is that what I had? Oh, ha. Okay. Yeah, so I didn't distribute the y, so that's y cubed. Okay, so that's going to be over 4. I was right the first time from 0 to 1. Thank you very much. So that's going to be minus 1 over 4. So that's just 1/2 minus 1/4 is 1/4. So that's just going to be 3 over 4, which is the correct answer. Okay, so I had it right the first time. All right, so, oops. So the domain, it looks like, yeah, so let's see if I can actually draw this now. So we have this circle and we have these strips going from here to here. But then if we look in the x, or in the xy plane, we have y equals x, and we have this. Okay, so these slices, basically it's going to be looking something, let's see. So we have y goes from 1 down, it should go to -1, except we're looking in this region here. So it can't actually go all the way to -1. It can't go all the way over here, because once we get to 0, that's our x bound. So basically this is our plane, x equals 0. If x is, this is the plane y equals 0, no. Okay, yeah, so think of it like a slice like we had before, but it kind of, the top kind of slants down till we get to 0 here at 0. Okay, that was a tricky one. a good example on why you should always draw the domains and not try to figure it out in your head, because there's no way I could figure that out in my head without drawing it. Okay, use spherical coordinates to convert the volume of the solid bounded above by this and below by the cone this. Okay, so if we have x equals rho sine phi cosine theta. You know what's really confusing is that in physics, like modern physics books, they have the phi and the theta switched, and it's really confusing. So this is sine phi sine theta, and z equals rho cosine phi. Okay, but so for this bound, we have the sphere rho equals 2. Okay, and then so just in general, we're going to have some sphere, and then we're going to have a cone. It's going to look something like this. Okay, but to do this, we square both sides, and we have z squared equals 3 times x squared plus y squared. I plug everything in, and I have rho squared cosine squared phi equals 3 times rho squared sine squared phi plus times cosine squared theta plus rho squared sine squared phi sine squared theta. Okay, cancel out the rows everywhere. Factor out the sine squared phi, and I have cosine squared theta plus sine squared theta. So I have cosine squared phi equals 3 sine squared phi. In other words, sine tangent squared is equal to 1 over 3, or tangent phi is equal to 1 over root 3, which tells us that phi equals 1 over pi over 6, like we saw earlier. Okay, so that tells us that this angle here is pi over 6. It's going to go all the way around because it's kind of symmetric about the z-axis. And rho is going to go from 0 out to 2. So that tells us our bounds. We have rho goes from 0 to 2. Phi goes from 0, the z-axis, to pi over 6. And theta goes from 0 all the way around to 2 pi. Okay, and we want to find the volume. Yeah. So we want to integrate from 0 to 2, 0 to pi over 6, 0 to 2 pi. And what are we integrating? Oh, if it was just x, y, z, then we wouldn't be integrating anything. But now we have rho squared sine phi d theta d phi d rho. Okay, so this is separable, so I can just write this as a product of integrals. So I have the integral of rho squared from 0 to 2 d rho. Integral of sine phi from 0 to pi over 6 d phi, integral from 0 to 2 pi of 1 d theta, or just integral of d theta. Okay, so that is 2 pi. That's this one. This is what is that? That's rho cubed over 3, so that's going to be 2 cubed over 3. And then integral of sine is negative cosine phi from 0 to pi over 6, which gives me 2 pi times 8 over 3 times cosine of pi over 6 is minus root 3 over 2 minus minus 1. And looks like that's going to be right. Yeah. So if I simplify, so if I factor out a 1/2, then this becomes 8 pi over 3, so 3, times 2 minus root 3, which is the correct answer. Okay. One second. Okay, set up a repeated integral that gives the volume of the solid, the first octant whose top is the plane x minus y plus 2z equals 2, and whose base is the xy plane. In the xy plane is the region bounded by these two curves. Okay, so in the xy plane, we have y equals 1/4 x squared, y equals 4, and the y-axis. So that's this region here. So this is x, this is y. And then what does z go from? So it says the base in the, so it says the first octant. So that's going to start at z equals 0. Then it's how high up is it going to go? Well, I'm just going to solve this for z. So z equals 1 minus 1/2 x plus 1/2 y. Right, I just solved for z because I know that z starts at 0 and it's going to go up to this. So I want to just set up the integral. So I'm going to integrate from 0 to 1 minus 1/2 x plus y dz. And then let's figure out, let's do y. So it's going to go from 1/4 x squared up to 4. So that's dy. And then we're going to go from x equals 0 all the way up to where these intersect, which I should figure out quick. So I have 1/4 x squared equals 4. So x equals plus minus 4. So that means that x is going to go from 0 up to 4 dx. And that's all it's asking for. It just says set up a repeated integral that describes the volume, and this will do just that. I hope they're in the same order. Oh, okay. So the way the solution gives it, this would be completely correct. The way the solution gives it, they just integrate this function, this inner function. So they use 0 to 4, integral from 1/4 x squared to 4, and they just, so integral of 1 is z, so if I do this inner integral, I get 1 minus 1/2 x plus 1/2 y dy dx. And that would have been exactly equivalent, because this is just equivalent to working out this inner integral. Okay. Oh man, time goes fast. It's already 8:08. Okay, so set up a repeated integral in cylindrical coordinates that gives the volume of the solid in the first octant, which is bounded above by... That got clipped. Okay, so those are supposed to be 2's. Yeah, so that's supposed to be a 2. That's supposed to be a 2. Below by the xy plane. So that means from... so this is z equals 0. And on the sides by the cylinder x squared plus y squared. Okay, so it just says we want this in cylindrical coordinates. So to convert to cylindrical coordinates, we're going to have z equals e to the negative r squared for this right here. And then this is going to tell us that r is equal to 1 right there. Okay, so if we draw the region, right, we have the cylinder in the xy plane. And then in the, let's just say yz plane, it's going to look something like, so I have the cylinder, the sides of the cylinder, and this is going to look something like this. So it's this region in the first octant. Yeah, in the first octant. So just this region up above. Okay, so we're going to have r goes from 0 to 1. So I know that 0 less than or equal to r less than or equal to 1. Theta is going to go from 0 here on the x-axis around to pi over 2. And then z, I know, goes from 0 up to this function. And I know that because it says it's in the first octant. Okay, so I can set up, does it say set up or evaluate? Set up a repeated integral in cylindrical coordinates. So if I want volume in cylindrical coordinates, I need to make sure to include the Jacobian term. So it's going to be r dr d z d theta. Hold on, I don't want to integrate with respect to r first because z bounds are given in terms of theta, or in terms of r. Right, so if I integrate with respect to z first, then I can do 0 e to the minus r squared, and then I can integrate with respect to r from 0 to 1, and then from 0 to pi over 2. If I had tried to put this as dr dz, I would need to rewrite the bound so it didn't involve r, which I don't feel like doing. Yeah, that's the same as the solution. A solid is bounded above by the surfaces z equals root y and y equals... Wait, what? Okay, so in the z or the yz plane, I have z equals 2 minus y. Oh, I see. Z equals root y. Below by the xy plane, and on the sides by the plane x equals 0. Well, that's the... Oh, that's the plane z equals 0, okay. And x equals 2. Okay, so we know that the sides, it starts at x equals 0, and then it kind of comes up out of the page to x equals 2. And it says find the volume of the solids. That's not that hard. So first I'm going to do the part that I can't really visualize. That's the x component. So it starts here at 0 and comes up out of the board to 2. So it's going to go from 0 to 2 dx. And then so I'm going to do it going this way first, because that way my bounds are the same for the top and bottom, and I don't have to write it as two different integrals. So I'm integrating first with respect to y. So this is the line z equals root y, or also y equals z squared. And this is the line y equals 2 minus z, and z equals 2 minus y. Okay, so y starts from this curve, z squared, and goes up to this curve, 2 minus z. And then z goes from 0, right, the y-axis, up to, where do they intersect? So we have 2 minus z equals z squared. Move that over, z squared minus plus z minus 2 equals 0. I know that factor is z plus 2 z minus 1. So that's going to intersect at z equals 1. Okay, so now we start evaluating. So this inner integral right here with respect to x does not depend on y or z. I can pull it all the way out, and that's just going to evaluate to 2, 0 to 1, z squared to 2 minus z, dy dz. And then I integrate this, and I have 2 goes 0 to 1 of 2 minus z minus z squared d dz. Okay, so I integrate this, and I get 2, that's 2z minus z squared over 2 minus z cubed over 3 from 0 to 1. Gives me 2 times 2 minus 1 half minus 1 third. Put it all over 6. So we have 1 third times 12 minus 3 minus 2. That's going to be 7. And I get 7 thirds, which is correct. Boom. Okay, I'm going to pause the recording.